Okay, let's get started. Fine, where are we? So let's review the Unruh effect. Unruh effect. So where are we? So we just consider that the accelerating observer B and U, and there's something accelerated observer like this way, and then who's the C is kappa B del B plus minus U del U. So that's our the constant acceleration. Okay. So that's our observer, and then we look at the Cragg-Gordon equation in this the metric. So U is given by B is given by xe to the kappa T minus sign. Here x sorry. So this is x is constant surface, and we call it this right Ringel wedge and left Ringel wedge. This region. This region called right and left Ringel wedge. And then we do so the Cragg-Gordon equation of U coordinate is very simple. So the Cragg-Gordon UV coordinate is the OR. So Cragg-Gordon equation of this x coordinate is something like this way: partial x and x partial x y and plus sigma square kappa square and phi equal to 0. And then so our solution is something like e to the minus I sigma t times minus p log x. So like this way. So that's what we saw in the so this is one of the solution, and then here we just consider the UP right moving is something like okay. So yes, sorry. Yeah, I mean, here it's just plus minus like this thing, maybe. It depends on the right moving or left moving, right Ringel wedge and left Ringel wedge. And then, so if you consider the mode in the right Ringel wedge, we have something like a CP, e to the I sigma over kappa, log minus U, 0, 0, and then CP, e to the minus I sigma over kappa, log B, and where this U is the less than 0 and B is greater than 0, 0, 0. So this is the mode that satisfies the Cragg-Gordon equation. So here, so U has to be negative. So this region, right Ringel wedge has U is negative and B is positive. Okay. I think E, yeah, B is positive. So here is a P is greater than 0 and a P is less than 0. Okay, so that's the case. So here you can easily see, I mean, just plug into this log, okay, log U, log minus U is equal to, what was that? Log minus U is something like minus kappa T plus log X, right? Like this way. And then if you multiply P, you get this one. If you multiply P times this one, then you get this one. On the other hand, if you consider log P, then you have the kappa T, and then plus log X, small x. So depending on sign of P, when P is positive, you can use log minus U. Okay. So depending on the P is positive or negative, one can use the either log minus U, log P in right moving sector. Right Rindle wedge. And then for left, so we just need to, so left, so this killing factor, not killing factor. So accelerating observer, so this become, so this here you just have the future directed, but in the left Rindle wedge, it become past directed. So in the case of this B, del B, and U del U. So here it's just past directed. So therefore, so here you treated this one as positive mode. So this is positive energy mode. But on the other hand, for left moving sector, so we treat this one as the negative energy mode. So that can be obtained by Cp log e to the I sigma over kappa log U 0, 0, and Cp e to the minus I sigma kappa log B, minus U. U and minus B. When the U is positive, U is negative, B is positive, and B is negative. In this case, P is greater than 0, P is less than 0. Okay, so that's the mode that satisfies the Graham-Golden equation. Okay. Fine. So that's what we saw. So this is a model from right Rindle wedge and left Rindle wedge. And we try to construct the mode which can extend it to the whole region of the Minkowski space. And that, yeah, anyway, so this mode, okay, so this can be written something like this way. So the BPR UPR of X plus BPL UPL of X plus the complex conjugate. So my complex conjugate means the annihilation creation operator U bar R P plus BP L dagger U bar L. So that's the model expansion for the. So this is P. Okay. So So they satisfy the complete basis so this mode satisfy complete basis. And then we can just mode expansion for this one. So on the other hand, we can just construct it such a way that the, so note that this U bar L or P can be written like this way. E to the I sigma over kappa log U. And then here, so you just write down the, let me just do the trick. Let me just, so this is log minus U plus I plus minus I pi and this one. Since the here you just put the minus sign. Here there's no minus sign, but you just put that. So this is e. This guy is e to the I pi. So therefore, to cancel you just put the e to the minus I pi, and then log e to the minus I pi is minus I pi. Okay. Right this way. Then this can be written as the. This can be written as the Cp e to the pi sigma over kappa log minus U. Okay. So now we can just connect these two modes. So P is positive, but U is negative is this guy. And then P is positive, and U is positive is this guy. And you can connect between, you can use between this U coordinate. For U, P is the positive case, we can just do the analytic continuation by just combine these two cases. So like this way. Fine. So then, so this is a mode which only depends on U. So and recall that the Klein-Gordon equation here, capital U is capital U, capital V. Klein-Gordon equation become like this way. So therefore, phi has to be homomorphic. No, it's if it is a factorized form like this way, so it satisfies the Klein-Gordon equation. Okay. If it is. So it's already a factorized form. So this model will satisfy the Klein-Gordon equation. So then, so this is one case. In negative case, one can similarly construct the UR. Minus pi over sigma over kappa U bar R LP, which is Cp pi sigma over kappa, and then e to the minus I sigma over kappa log minus b. Okay, so like this. If you do the same trick, one can just write down the mode, which only depends on capital B. So therefore, this satisfies the Klein-Gordon equation. Klein-Gordon equation. So, and then we call it, so the appropriate normalized, this appropriate normalized form of this one is we call it B1. We call it this one is B1. B1 of P. And then, oh, sorry. So this is the opposite. Sorry. Yeah, sorry. So this one we call it B1 or P, and then And we can just also construct a UL of P plus E to the minus pi sigma over kappa, which is something like Cp E to the minus pi sigma over kappa E to the I sigma over kappa log minus U when P is positive. And then here is just some number, Cp E to the I sigma over kappa log minus V, and the P is negative. Okay? So this is another mode which satisfies Graham-Golden equation. And we call it this one is equal to, this one is equal to B2P. Okay, and then we just do another mode expansion, which is okay, which is the valid in the entire Minkowski space. So AP2 of BP2 of X plus conjugate, complex conjugate, like this way. And the Minkowski vacuum is just annihilated by this mode. We define like this way. So we define like this way. So now, so we just try to find a relation between this mode and this mode, or this mode, and it turns out that so this BP R is given by square root 2 sinh of pi sigma over kappa, and then e to the pi sigma over 2 kappa AP of 1 plus e to the minus pi sigma over 2 kappa AP 2, like this way. So that's the consequence of the, I mean, just so this guy is the UPR dot phi, and we know that the UP can be UPR can be written in terms of BP and then BP1 and BP2. So therefore, this is in fact BP1 phi, and this one is BP2 and phi, inner product. Okay. So therefore, if you know the relation between U and the B relation, one can just obtain this. Then we can do a similar thing for L, in fact. So here we just have the same 2 sinh pi sigma over kappa. Okay. And you must obtain the opposite. Shall we try to derive that? Okay, so let's do that. I think I didn't write down the note. So that this is equal to U R bar and P, right? Okay. Sorry, so this is B bar. Dagger. So this is dagger and B bar. Okay. So B bar and dagger. Shall we try to do that? I mean, here it's not written in the note. So this one should be equal to. So this one should be equal to what? So UL of P of phi. Okay. And how do you get the UL? So B2 is equal to this one, and B1 is equal to UPR plus e to the minus pi sigma over kappa U bar LR, right? Okay. And to to get, so we want to have this one. So therefore, to get this one, what we need to do is that so you just take a complex conjugate. Okay. So complex conjugate and just complex conjugate, and then you need to multiply here. Is that so you need to multiply. How do you get this one? So okay, most likely what you need to do is the e to the pi sigma over kappa url of phi, and then oh, I understand. Oh, I understand what I should do. So most likely. So what you need to do is that, so B1 or P, right? Can I? To get that, so we need to get rid of this guy. So to get rid of this one, so what we need to do is BP of 2 times e to the pi sigma over kappa, and minus B1 or BP of 1 bar, right? Okay, and then you can just remove this one and then divide it by some approximate power. Approximate power should give you some number times UPL, right? So therefore what you get is that now I understand what I should do. So what you get is something like this one. Square root 2 sinh pi sigma over kappa, and the same factor e to the pi sigma over 2 kappa, but now a2 of p plus e to the minus pi sigma over 2 kappa, and a1 of dagger of p. That's what you get from this calculation. From this calculation. Okay. Fine. So we can just do the same calculation for dagger case. And what you end up with as follows. So for instance, A1 of P can be written as some combination of BP. A1 can be some combination of BP R plus B, L, P, dagger, some number. I'm not going to derive this one. So if you just write down if you try to get the A1 out of here, so you just need to take a combination of BPR and the BPL dagger. If you take a dagger, so this becomes like this. So this means that and we know that this one will annihilate vacuum. So this is 0. So therefore BPR plus some number, BPL dagger, annihilates vacuum. Okay. Is it okay? So this means that as follows. This means that if you have a Lindner space, right? So here, right Lindner wedge and left moving wedge. Here in right moving, there is an annihilation happen. Annihilation happen in the vacuum at some point. But here you have a creation will happen. Creation. I mean the reason why I put it like this way is that maybe it's okay. So creation will happen here. So in the Minkowski vacuum, it's generally it's defined by A annihilates to 0 because this is an annihilation operator. But that is just we'll give you an annihilation operator and a creation operator on the right and left Linder wedge. So therefore, there's something going on in the even if it's a Minkowski vacuum. So right moving sector, not right moving Linder wedge, you have a particle annihilation occur, but at the same time, so the particle creation should happen in the left Linder wedge. So it's a very right and left Linder wedge is entangled, highly entangled in this case. Okay. So now, so we just consider some we just focus on this right Linder wedge to see what's happening in the Minkowski vacuum. To see that, we just look at the numbering operator of like this way. Okay, and then we just have the e to the minus pi sigma over 2 sinh pi sigma over kappa, and then 0 m AP Dagger, AP2, AP2 Dagger, and 0 m. Okay, so I just plug this one into over there, plug into that one over there, and this is equal to the appropriate normalization. This is equal to 1 over e to the 2 pi sigma over kappa minus 1. Okay, so that's what you get, and this is exactly the Planck distribution. With the temperature is given by the kappa over 2 pi. I mean, if you want to restore the Boltzmann constant and the Planck constant, one can have like this way. Okay. Distribution with temperature is given by the surface gravity. Okay. So therefore, this means that if you have a Linder observer, even though it's a Minkowski vacuum, so Linder observer is like this way, will feel some amount of particle. So this will receive some amount of particle. So here he receives some. I don't know how to draw. I mean, okay, maybe I think it's better to write down like this. Some amount of particle is something like this way. And here he receives some amount of particle like this way. So this is the thermal state, some amount of particle. So what kind of particle do you receive? So one student asked me a question, what kind of particle is this? What kind of particle is this? Do you receive? Can you see that? Is it like a boson, fermion? If it is a boson, what kind of boson? If it is fermion, what kind of fermion do you receive? Some amount of a particle. Can you see that? So this is numbering operator. This numbering operator is the numbering operator of what? So what kind of so essentially this distribution is created by this part this creation and annihilation operator. This creation operator creates what kind of particle? Huh? Yeah. Yes. So this guy is the create a scalar boson with how to say the momentum p. Okay. So the reason, so this will the particle, since we consider only the action Lagrangian is given by whatever some number times g mu nu partial mu phi partial nu phi. Lagrangian is this guy. So therefore, what you receive is that the particle is a free boson. Spin zero scalar boson you will receive. But if you change Lagrangian, you will receive another particle. So it depends on Lagrangian you consider. So the answer is here. So anyway, so whatever computation you do, then you will receive. I mean, it is the reason why I use the free scalar is that it's the simplest. But if you can do the same computation for Dirac field or whatever, the gauge field, the procedure is more complicated, but you have to do, you will get the same conclusion. Okay, good. So this Planck distribution means that the right Rindra wedge, the density matrix right is given by as follows: the sum of infinity n is equal to 0 p z divided by e to the minus beta e n and p and p. So density matrix become like this. So this is similar summer radiation of the with temperature whatever temperature given by beta 1 over beta. And beta is given by 1 over kBt, and in our case 2 pi over h bar kappa. So that's the case. So here, so this means that the right. So here is you get. I will explain more detail. Well, that you get a mixed state. Okay, it's not pure state. It's no quantum mechanics mixed state you will get. To get this one, so you have to have the following configuration. So where the n of r. So this is the right. I call it. N is a numbering operator. So p is given by br. P dagger n times of 0. Rindra vacuum. The same thing. So NL of P is given by B L P dagger to the N 0 Rindra. Like this. So to get this one, so in fact the Minkowski vacuum. So this is actually exercise homework. The last problem you have to solve. The vacuum. So 0 Minkowski vacuum should have the following form. So this appropriate normalization, which is not important. N equal to 0 and infinity e to the minus n pi omega over kappa and R of P and times and L of P, like this way. So that's the essentially what you need to do is e to the minus whatever beta en right tensor en left. Essentially this is a form of the Minkowski vacuum. So note that these states are defined using Rindra vacuum. Since Rindra vacuum is different from the Minkowski vacuum, so Minkowski vacuum is written in some kind of coherent state in terms of right and left Rindra wedges. So this can be, as I mentioned, so Minkowski vacuum is just defined I analysis like this way. Okay? And in fact, as I mentioned, so this can be written as the either right of P plus some number times BP left bar dagger of like this way, like this. So if it is one, like if it is this way, and two, you have to swap left and right and so on, left and right and so on. To satisfy this one, so you have to have this kind of coherent state for any mode P and so on. So that's what you need to show in the homework. So this means that it's really highly entangled. So you have right and left. Okay. So here, so the vacuum is that it's just that if you observe some states in the if you observe states in En, okay, if you observe states in En, so left is right. In left hand side, you also should have somehow created the same states in the left Rindra wedge. It's highly entangled. This means that since it's really the same states, some of the same states, so therefore once you observe the states in a right Rindra wedge, so the same states should be created in left Rindra wedge. So therefore right and left Rindra wedge are highly entangled. So this means that the entangled state, entangled. Okay. So the next lecture, I'm going to talk about how do you just measure how much it's entangled they are from the next lecture. So that is called von Neumann entropy and so on. But that's yeah. So therefore, so the Minkowski's case, even though it's a vacuum, but if you change the basis of the observer, so you get the highly entangled. The vacuum is highly entangled. That's the conclusion of the Bohm-Rundle effect. Any question at this moment? Okay. Yeah, so to show this one, you have to use this guy. You have to use this one. Okay, so now we'll move on to the Hawking radiation. But before that, let's recap what we have seen. So what we have seen is a black hole. Is the thermodynamic object. Especially, so we have the so what else do you have? So if you change the mass, what kind of change do you have in general? So black hole's mass, and then what else? What kind of,
Charge.
Okay, charges, phi of h dq. What else? Black hole is characterized as three quantities: mass, dj, and omega h. Okay. So that's the first law of black hole thermodynamics. Okay. And in particular, S is given by area divided by 4. Okay. And the Hawking temperature is kappa divided by 2 pi. Okay. Kappa divided by 2 pi. So that's the first law of thermodynamics. First law. So here, this S is equal to A is called Bekenstein-Hawking entropy. Entropy. And in fact, this is called Hawking temperature. Hawking temperature. And this, yeah, so the question was asked by actually, sorry, historical. So there is I cited the historical essay about this Bekenstein-Hawking entropy and so on at the beginning. So what was that? Yeah, actually, Weinstein. Yeah, actually, it's very interesting. I read this one briefly, but Weinstein and 2102 11209. So this is the Arcana number. So you can, so there's a historical account about the black hole entropy. So the first actually question was asked by Wheeler: if you throw the cup of tea into the black hole, the cup of tea has entropy, what happens in the black hole? Unless black hole has the entropy, it breaks a second law of thermodynamics. And Bekenstein proposed that black hole entropy is proportional to A, proportional to area of horizon. And then after that, the Hawking and then his graph later is proportional coefficient is 1 over h, no, 1 over 4. And of course, there's a bunch of factors up here. I said that G is equal to H bar equal to KB equal to 1. So all the quantity appear in here. So G and KB and H bar. What else? Yeah, I think that appear here in this formula. But I just set everything to be 1. Okay. So that's actually that's a kind of remarkable that the first of all, the entropy is proportional area is kind of remarkable. So if you could just consider the usual thermodynamics object like a cup of tea or whatever, or this air or whatever, usually this entropy, usual thermodynamic object. So entropy is proportional to volume. volume of an object. Okay. So, but in this case, the black hole, the gravitational case, black hole entropy or gravitational entropy proportional area. That's already like striking. That's already so. So this is the something called holographic principle. So all the how to say micro. So if you believe this entropy is a kV times log number of state, all the degrees of freedom is somehow restored at the event horizon. Okay, it can be somehow. So therefore, you don't need to know about the bulk interior of in the black hole. That is called holographic principle. Furthermore, it has a temperature. It has a temperature. So if it has a temperature, you should have the so-called black body. Black body thermal radiation. Okay. So black hole thermal radiation. I mean, this is exactly what the Planck has found. Or Planck distribution, whatever you call it. Planck, with the Planck distribution. So I read this essay that the first the Hawking disagree. This is the idea that the black hole has a temperature, but somehow he changed his mind, and Hawking in 1974 or 75, the paper, Hawking apply QFT in curved space-time. To show that indeed black hole has a thermal radiation. That's what we are going to see from now. Okay, so that's what we are going to see from now. Okay. So this one, this one is actually the first progress made by Strominger-Baffa and Baffa in 1996 by using string theory. So here, and after that, repeatedly they do a similar computation, more refined computation by Strominger-Baffa to reproduce Bekenstein-Hawking entropy. Black hole entropy or whatever BH, I don't know which black hole entropy, to count microstates, just number of microstates to reproduce Bekenstein-Hawking entropy, and this one is so far successfully done by so-called supersymmetric black hole or extremal black hole. So extremal black hole surface gravity is 0, so therefore Hawking temperature is 0. Hawking temperature is 0. Hawking temperature is 0. So therefore it has some kind of stability. So anyway. So then let's do the Hawking calculation. Okay, so let's recall. So let's recall the Schwarzschild. So we just use Schwarzschild. So I just want to use. Okay. So Schwarzschild, this is I plus and I minus. And then here we have a geometry something like ds square is equal to 1 minus 2m over r dr dt square minus plus inverse dr square plus r square d omega 2. Okay. And then we can just use change of variable. So classical like coordinate will give you like this way. du dv plus r square like this way. Where u is given by t minus r star, and this is the t plus r star, and r star is the tortoise coordinate, which is 2m. I don't know. Okay. 2m minus 1. Okay. That's what we had before. And then now we just again apply the QFT in group space-time technique to solve it. So the we consider only this the action is given by d for x square minus g, and then g mu nu partial mu. Okay, g mu nu partial mu phi. So we just consider scalar action and solve the Cohen-Gaudian equation. Okay. To solve Cohen-Gaudian equation, we just do some spherical harmonic expansion. So okay. So at each point of Penrose diagram, what you have is what? At each point stands for what? S2. Yes. So S2. So therefore, so we can just have the orthonormal coordinate for S2 direction. So this S2 direction to have like this way. So the phi of x is sum over L of m 1 over r phi of L t r y L m omega. So this is the spherical harmonics. So L is the total angular momentum. M is the eigenvalue at the z-axis. And then so this is what you have in the spherical harmonics. So you just expand in terms of this spherical harmonics and the mode, so that the Cohen-Gaudian equation is in fact du and dv act on plus bl of r and phi l dr is equal to 0, where bl of r is given by 1 minus 2m divided by r, and then times l L plus 1 divided by R squared plus 2m divided by R cubed. Okay. So that's the what you obtain from the Klein-Gordon equation. So this is become Klein-Gordon equation. Klein-Gordon equation. Here it's totally fine to change this one is equal to phi t square minus phi del r star square. That's also okay. So it's the same thing. But now instead of the potential is coming from really angular momentum of the spherical harmonic. And this pi L is really this pi L. It's a modal expansion. Okay, let's look at that. So this potential becomes BL of R goes to 0 when R goes to infinity, of course. Once you look at the R goes to infinity, so the R goes to infinity is scribe plus or scribe minus is the R goes to infinity limit. And then this part becomes 0. So there's another limit, this BL goes to 0. So the potential goes to 0 when R goes to horizon. If R goes to horizon, this term will become 1. So therefore, first term is 0, right? So therefore, then if you two extreme regimes, so if you go to the no infinity, so the scribe plus or scribe minus, or if you go to the horizon, here is R equal to 2m. So this one is the R equal to 2m. The potential becomes 0. So that's the observation. So therefore, so around the horizon and then around the phi infinity, it behaves like a really free Klein-Gordon equation. So you can ignore BL of R, and you can see that it's really like the Minkowski Klein-Gordon equation. So therefore, if you just consider asymptotically, R goes to infinity, or R goes to 2m, so the equation becomes like this way. Phi L is equal to 0. Or it's the same thing. Equal to 0. Okay. Okay, so this means that the phi L has a modal expansion around this region. So around this region is something like e to the minus I omega u, or e to the I omega v, like this way. Yeah, as a positive mode, And then this is e to the minus I omega t r star minus e to the minus I omega t plus r star. Okay, r star. And then here we call it, this is outgoing. And this is the ingoing mode. Okay, so which direction? So here you have a b direction is to this direction as always, this cross type, and u direction is this direction. So when u is equal to constant, u is equal to constant, you have this direction. These are U is constant direction. And B's constant direction is this direction. These are B's constant direction. So therefore, this assignment is okay. Okay. Fine. Then we can just have the in vacuum. So here we just have in vacuum, 0 in vacuum, and 0 out vacuum. Okay. So and then we just want to compare between these two. So to define the 0 in vacuum, again, we just do the model expansion of the Klein-Gordon field around here, and just find the A, analyze the 0 in equal to 0. That's what we want to do. And here also, we just want to define 0 out by model expansion of outgoing mode by B acts on 0 out equal to 0. That's what I want to do. That's always. So here you have a different vacuum, and we just want to find a relation between A and B over there. Okay, so that's what we want to do. Okay, so that's what I want to do. But okay, to do that, where should I erase out here? So here, so we just do the model expansion is something at the scribe around the path infinity. Around the path infinity, we have a model expansion fi of x is something like e to the minus I omega b divided by 2 pi omega r square root y lm in omega. And then, so this has the following property. So we just define like this way, as usual, delta I prime, which is the delta omega minus omega prime, del L prime, del M prime. So I stands for omega, L, and M, F. Okay, so that's the mode expansion for the Karuskal-Klein field. And then phi of x can be written sum of AI Fi plus AI dagger Fi star, like this way, and sum of I. So that's the usual story we have, and then we define in vacuum is as usual, where equal to 0 for any I is the omega, L, and M. So that's what we have done. Okay. And then so what we want to do is the following. So here it is a Cauchy surface of this geometry. I minus is a Cauchy surface. Okay, Cauchy surface. Do you remember? Any point of the causal curve. So pick any point in the space-time, and the causal curve will Yeah, causal curve should just eventually hits to the Cauchy surface. For instance, like this way, and the causal curve is something like this way. I mean, the light is will go like this way. Okay. So therefore, any point, pick any point. If you do the whatever causal curve, at the end of the day, you start with you have to start with path infinity. That's a Cauchy surface. For past infinity, another Cauchy surface we will take is as follows. So this is H plus. This guy is H plus. Horizon. And then scribe plus. And it's just future infinity. That's another Cauchy surface we will take. And then what you have is the following mode expansion. So P of I of x is a mode expansion e to the minus omega u divided by the same mode expansion. Okay, same mode expansion like this way. This is the mode expansion on scribe plus. On the other hand, you will have, so this is a mode like coming like this way, outgoing like this way. On the other hand, we have to find the mode which is the incoming like this way. So this is Pi, and this is, I call it Qi for horizon. So the Qi of x is a mode on the H plus, but supporting the H plus. Okay. And then we just do the mode expansion of the Klein-Gordon field, sum of I, AI, not AI, BI, PI, plus conjugate, complex conjugate, and then CI, and QI, plus CI, dagger QI star, like this way. So you have a mode expansion. And then so out vacuum is just defined by Bi of 0 out is equal to 0, and also Ci acts on 0 out, vacuum to be 0, like this way for any I. Now, so we just want to know the transformation from this Pi and Qi and the upper one, Fi. Okay. So these are complementary the orthonormal basis we take. So therefore, we want to see that some linear transformation between them. Bogoliubov transformation. So this Bogoliubov coefficient will tell you about the Hawking radiation, in fact. So therefore, we just write down Pi of x is something like whatever. Sum of it's a Bogoliubov transformation. JFJ plus beta ij and fj star, and Qi of x is some other expansion, gamma ij fj plus eta ij is fj star. Okay, like this way. So this is the Bogoliubov transformation. If you use this one can just relate to Bi and then Bj, Bi bar dagger is given by alpha star, beta star minus alpha, minus beta, and alpha, a dagger. And the same thing what happen in the it'll be CI mode. So we can do the same thing for the CI. So we can relate. So A dagger to B or C. C dagger. I'm not gonna write down everything, but what we want is that we just want to measure 0 in is a vacuum of the vacuum at the past infinity, even though vacuum past infinity, what's going to happen when it measured numbering operator at the future infinity. Okay, that can be done by just putting numbering operator B dagger I B 0 in. Okay. So this can be done by just putting numbering operator BI. Okay. And then this is indeed will give you sum over beta. I mean, this one is already derived the last time, so in J, like this way. So that's the yeah. Okay, so that's what we want to compute. That's what we want to compute. Okay, so yeah, so and here, so that's what exactly Hawking did. So we for the fourth calculation. I mean, it's totally valid computation. I mean, at phi infinity, it's really Minkowski space, but there is a gravitational collapse. So whatever gravitational collapse of a star is something like this way. Star is something like this way, or whatever this Baedia construction is something like there is no infalling matter. It's just a really high density no ingoing matter into here, and to create a black hole. That's also okay. But below them, it's just really Minkowski. It's really Minkowski. So that's a Baedia, how to say, infalling, no infalling object. But to create whatever is okay. But phi infinity, and so you should have the Minkowski vacuum. But after the gravitational collapsion, there is space-time highly curved. After that, so we want to measure what's happening in the far future infinity. That's what we want to do. Okay, before doing computation, let's take a break. And we want to compute this beta from now. Okay. So let's take a break. shall we resume? It seems like many people are tired already at the end of the semester. But you guys do not take so many courses, right? Do you need to? Some students need to. Fine. So what we want to show is that this guy. We want to show this guy. So to do that, I just want to do the following the approximation. So here, so instead of do the approximation, so the pi, so as I mentioned, fi of x is approximately e to the I omega b, and then minus divided by some power, and then spherical harmonics. I think that's what I want. Lm, and pi of x is e to the minus I omega b, no, not b, u, divided by some number, and ylm. Approximation we had like this way. But instead of that, so we just write down more precisely. So here we just have something like I'm so stupid. So the p omega w, p omega l, small p, capital F, omega l, and the capital P. This is small p, omega l, and then the overall factor is 4 pi omega r. Okay, that's what I wrote. Sorry, I think it's a small one. My note is small p and small f. So this depends on the r. This depends on r. This depends on r. Depends on r. Okay. And then what we want to compute is the alpha and beta and so on. So to do that, we just need to just take an inner product. So alpha I. So did I? Okay. So alpha I is the pi of x acts on the fj. So this one is alpha ij, right? Am I correct? Yeah, it should be okay. Star. It should be. Okay, and then here we should have to get the beta fj of p I of x is a beta ij. Sorry, so maybe ij is something like this way. So that's what we have for. So to do that, so therefore this is equal to its appropriate normalization, which is not important, minus infinity dB e to the I omega prime b p omega l t l at the scribe minus, and this one is also given by dV e to the minus omega prime b P omega L T L and square minus. Okay, so everything, so the inner product is defined for alpha and beta is this the past infinity here. So inner product is defined here. So therefore, everything needs to be valid here, the past infinity. So the I and J, so I don't know, I is equal to omega, which one is correct? Omega L, M, yeah. And then J is equal to omega prime, L prime, and M prime. Of course, here, when you take an inner product, there must be del L, L prime, del M, M prime is assumed. It's like this way. So, but I'm going to omit this boring part. Okay. Now, one side of it is that this PI is you have to be careful about it. So PI, so you have to be careful about this PI. So the one thing we have is that there is something like from infinity to, you don't just by angular momentum using, so this potential, so this BL of R is something like 1 minus 2m over R, and then L plus 1 divided by R squared plus m R cubed, like this way. As far as we go, 2m R cubed. So if you have an non-trivial angular momentum, it has create some potential. So therefore, there is some particle starting from past infinity, and by doing, due to this the barrier of the potential due to the angular momentum, it just goes to the future infinity without just without seeing the effect of this horizon or the gravitational effect. It's purely due to this angular momentum barrier. So due to the angular momentum barrier, there is a reflected to the future infinity from past infinity due to the angular momentum barrier. So we want to omit this kind of mode. So to do that, so we just need to so Pi of x is we just get rid of this mode by Pi of 1 of x plus Pi of 2 of x. Such that here it's just this guy is reflected. Prefer this color. This guy is reflected by the external potential B of L of x, but this guy is really the one which appear like this way. So you just have start from B here, and penetrate inside a star, and go into infinity like this way. So we want to find such a star. So what we are going to do is that we just want to compare between the mode here and the vacuum here. Okay. So therefore, we need a geodesic, null geodesic, such that which connected between these two regions. Okay, between these two regions. To do that, we just really need the null geodesic like this one, and which really see the effect near horizon. Okay, In my note, I call it this one is gamma. So the gamma is the geodesic, new geodesic, which just starts from B here, and which is less than B0. Has to be B0. B0 is literally the one that hits the start of the horizon here. Okay? Unless otherwise, I mean, you cannot. I mean, if you just go inside a B0, it enters the horizon and it hits the singularity. So therefore, it has to be below B0. Okay. So we focus on. So this is the one I wrote. This one. So this is the one I draw like this way. So this guy is a PI. Pi of x of 2. So we have to separate mode, and we need to ignore this guy. So this is only the P2. P2 contribution is the only contribution for Hawking radiation. Okay. And now, so we just take a look at the gradually how to connect U and V. Okay. So here, so as you know, P of I has the dependence on U here. So dependence on U. This is exactly what I wanted to avoid. So remember, so the P of I has the dependence on E to the minus I omega U, like this way. P to the minus I omega U. And we want to see this I omega U dependence by solving a Newton-Geodesic equation. Solve Newton-Geodesic equation. So strategy is to solve Newton-Geodesic equation and write down U, a relation between U and affine parameter. Find affine parameter. Lambda. So the first, that's what's going to do. And after that, we want to try to compare lambda with B. Okay. In that, if you do that, so here you clearly have the dependence on U here and dependence on R here, and it's not clear that how this P omega L depends on B coordinate. So here we have to integrate over B. So good coordinate around here is a B coordinate. So B coordinate. We have to do the integration of this to take this inner product. Take this inner product. So we have to perform V integration. But now here we have a good coordinate is U. So the propagation mode is really measured by E to the minus omega U. Okay? So therefore, we have to somehow relate U and V in nice manner from a different region. That's the difficulty of this computation. And to do that, we have to solve the Newton-Geodesic equation. Okay, so now on the Newton-Geodesic equation, we already solved many times in the short. The first of all, so if you have the x dot of mu is equal to k mu, so here dot means the derivative with respect to affine time. So affine time is a Newton-Geodesic equation, lambda, like this way. Then conserved quantity. How do you measure conserved quantity? Huh? Energy and angular momentum can be obtained by just contract with the Killing vector. vector. This is conserved quantity. This is quantity. So if you take C as the partial T, you get the energy. C is the phi. You get the angular momentum, which I call it somehow J. Okay. Maybe okay, erase this part. And then geodesic equation can be Newton's geodesic equation can be written as like this way. This is already did homework as a long time ago. You guys just did over R, and then the phi of the lambda is equal to J of R square sine square 0 equal to 0. And now we can set. We want to avoid the case that the due to the angular angular momentum potential, this guy, the particle is reflected into the whatever, into the infinity. So that's what I want to avoid, this kind of situation. So that this one I set J equal to 0. So J equal to 0, and I want to solve this guy. And then, so since the G mu nu x dot nu equal to 0, so this will tell you that this one is equal to, how do you solve this one? This one square 1 minus 2m over r square minus e divided by this guy, this e? No, square here. Plus what I'm doing here, 1 over square dx d lambda square, right? Equal to 0. This is equal to 0. From here, dx over d lambda is equal to plus minus, not dx, dr, sorry, dr, okay, dr over d lambda has to be plus minus of e. So that's the geodesic equation tells us. So plus is outgoing. This is ingoing. As easy see, if it is r is decreasing, this is ingoing, right? R is increasing, is outgoing. So therefore, the change of R is positive, is outgoing, and change of R is negative, is ingoing. That's very obvious. So combine this equation. So d lambda t minus plus r star equal to 0. Okay, this is equal to du alpha psi is this one is equal to 0, or dv d lambda equal to 0. Okay. Is it okay? So so let's recall what's tortoise coordinate. R star is defined as the r plus 2g, no, not 2m. I don't know why I restore r and g here. Minus 1, like this way. Therefore, dr star divided by d lambda is equal to dr d lambda 1 plus 2m divided by this one, r over 2m minus 1. Do you agree with me? Do you agree with me? then if you just do the computation, this one is equal to dr, d lambda, and 1 over 1 minus 2m over r. Am I correct? No. So sorry, so what's the computation? 2m minus 1.
Denominator should be r minus 2m.
Denominator should be
Yeah, r minus 2m.
denominator r minus 2m. That's true. R minus 2m. Yeah, that's true. Okay, good. So then it's okay. Then it should be r minus 2m divided by r minus 2m plus 2m is equal to 1 minus r over 2m. Okay, so 1 minus r over 2m. And that's how total is coordinate is created. Okay, so therefore, if you combine with the dt d lambda is here, okay, and then multiply this guy, then we know that the dr d lambda is e plus minus e here. Okay, so therefore this guy holds. Is it okay? So as I mentioned, so this is dt d lambda minus plus what was that? dr d lambda and 1 minus 2m over r equal to 0. Okay. And we know this dt d lambda is given over there. And where did I make a mistake? Ah?
Are you sure that the calculation is correct, the last line?
Wait. This one?
Yes, yes.
R minus 2m, r minus 2m plus 2m is equal to r over r minus 2m. This is equal to 1 over 1 minus 2m over r. Thank you very much. Inverse. Yeah. Inverse. Okay, inverse. So therefore it's okay. Okay, fine. Thank you very much. Okay. Fine. So therefore, from here one can just find the relation between u and lambda. Okay, so then, so if you consider the case so better, so if you try to compute the du d lambda, I got confused. Sorry, just a moment. Sorry, so what I'm doing here? Sorry, so then d lambda, dr over d lambda is equal to minus epsilon, right? And then sorry, sorry, I got confused. What I'm doing here? So I just want to show that the u. Okay. So I want to show this one is equal to OM lambda. How do you show this one? No, sorry. This is U. So here I just want to show dV is equal to d lambda equal to 0. So I want to use this one. So here B is constant. So here B is constant. So B is constant. And then U is just a decreasing here. And I want to show this one. And I got confused. How do you show this one? Yeah. So sorry. So du d lambda is equal to d dd lambda t minus r star. Okay. And dd lambda minus wait, where did I put dr d lambda and 1 minus 2m over r inverse, right? Inverse, that's what we show. And here now have the so it's now ingoing. So here now ingoing one. So I just want to use this one. It's minus sign. So therefore this is equal to minus e 1 minus 2m over r. And then this is plus e. Oh, it should be 0. What was that? Sorry, I got confused. dr over d lambda is ingoing. Sorry, it's sorry, I thought this is equal to minus epsilon 1 minus 2m over r. Okay, that's not good. That's not what I want. I think sign is somehow strange. Sign is somehow strange. and I don't know how to fix it. Because u is needs to change right here. So u is keep changing here, right? So b is constant and u is inside. So therefore this should be non-zero for ingoing. This should be non-zero for ingoing. And then dr star over d lambda is correct calculation is this guy, right? It should be okay, right? Sign somehow strange. If it is ingoing, it's minus sign. Dr d lambda. This is if you minus sign. Then I think this should be plus. Then it's okay. Then it should be 2e divided by 1 minus 2m over lambda. No, over r. Over r. Somehow sign strange, so let's accept it that this one should be plus. Otherwise, sign is very strange. Let's accept this is plus. Okay, otherwise it's strange. Okay, and then this one is equal to, so du d lambda is the 2e minus 1 minus 2mr, and we know that the dr divided by d lambda is minus epsilon. So r should be equal to minus epsilon lambda minus e plus some constant. Okay, so that's the case. And plugged out into here, 2e minus, then you get a 2m over lambda. Sorry, 4m over lambda. That's okay. That's okay. Okay, so somehow sign strange. So sorry, I will check it later. So let's accept this one and then let's accept this one. Okay. So plug this one into here and do the Taylor expansion. Do the Taylor expansion. Okay, and then you get this one. Okay. Okay, if you solve this one, you will get the following equation. U is equal to 2e lambda minus 4m and log lambda divided by c. Okay. So that's what you get from by solving this equation. This equation. Okay. So where c is some positive quotient, c is some of the positive quotient, coefficient. Okay, and then we can set the near horizon. H plus is at lambda equal to 0, so we can just set lambda equal to 0 around here. So here lambda equal to 0 at the horizon, and then lambda is negative for outside the horizon. So therefore, near horizon, so u is approximately 4m log of lambda over c. Lambda over c. So that's what we obtain from here. Okay. So from here, so you can get the relation between u and lambda. near horizon, near horizon. So that's what you get from this calculation. So now, so we just put the this one into the previous model expansion for P. So P of I. So P of I of X is something like a P omega L e to the minus I omega U divided by square root 4 pi. 4 pi omega r. And YLM. You plug this one into here, this part will become e to the e to the 4 pi omega m log lambda over c. That's what you get from here. With E, U is like this way. There's a sign's missing, sorry. So sign's missing. So this is minus sign is missing. So that whole plus is okay. Okay, there are lots of typo in my note. So the sign is okay. This is a minus sign. Okay. And this is the case. Okay. So what we saw is that so here, so lambda equal to 0 around here, we already know that the u is can be written like this way. Can be written here. So what we saw is that maybe I can erase here. Maybe. So I just write down like this way. So from this calculation, so here we just consider ingoing null object, and from lambda around this distance. From here, u is around 4m minus 4m log lambda over c. So that's what we saw from this calculation. And furthermore, so what we are interested in that the geodesic jets connect from this region to this region. So B and B0 is here. So if you look at this geodesic here, around here, so we can just approximate that the B and B0 has the proportional. So if you only look at this region, so this region, okay, maybe I can use. So here, so we can just approximate around this region, approximate the B lambda. Lambda is proportional to B0. so it's proportional to linear to lambda. So if you just use this approximation, so this wave function here can be written as the following way. So p omega 2 tr is proportional to exponential of the I omega kappa log b minus b0 divided by some constant cd, like this way, when b is less than b0 and b is greater than b0. That's what should happen for this kind of geodesic. Then now also we just can connect this. Unfortunately, I already erased. So P2 of this amplitude written here around here just can be written traced back to the coordinate B now. So then we just need to just do a computation. So so as you recall, alpha j is just given by proportional to some coefficient minus infinity to infinity e to the I omega prime b, and this is P2 omega tr. The same thing. So beta ij is proportional to minus infinity to the infinity e to the minus I omega prime b P2 of omega tr. So that's what we want to compute. And we want to compute this beta to get the Hawking radiation. Okay. The Hawking radiation. And then, okay, so I think it's a calculation. It's kind of use gamma function and so on. So it's kind of tedious. So that I just want to give you a last result of this computation. Okay, so then substitute this equation to the following equation. So here, so if you just do the computation, what you end up with as follows: this omega prime is equal to e to the pi omega over how to say kappa and beta 2 omega prime, like this way. And from there, so one can just compute the numbering operator z in of the b I dagger and the b I or 0 of in, like this way. From there, so one can just compute this one is as follows: the some amplitude of gamma I divided by e to the 2 pi omega over kappa minus 1. Okay, so this is a computation we can do. I mean, so this step is kind of tedious. I mean, from this step, one has to use some special. So plug this one, this quantity into here, and do the integration. That computation is a bit tedious, so I'm going to omit because it's a gamma function involved. But the important thing is it's a ratio between alpha and beta. It's given by here. So this is it. In fact appear 2 times. The square of this term will appear in here. So as we saw in the previous calculation, and then at the end, the calculation. At the end of the day, this is a Planck distribution. With the temperature given by Hawking temperature kappa over 2 pi. So that's what we saw from this calculation. So this is exactly what Hawking did in our original paper in the calculation. So that's and here, so this gamma is in fact given by sum over alpha square minus sum over beta square with the ij and the times j plus j. So this is called a gray-body factor. Gray-body factor. It's not completely black. So somehow there's an effect. Amplitude will be affected by the gray-body factor, and so on. Okay. So that's the computation Hawking did. So from here, so what we have learned is that really there is some radiation of the particle when you consider the QFT in curved space-time applying on Schwarzschild black hole with the Hawking temperature, and there is often it's very, very kind of controversial that but people often use this metaphor. Actually, Hawking paper, there's a paper. This derivation is the CMP in Communication Mathematical Physics in 1975. But there is Nature paper, black hole explosion or something like that, 1974. This one is clearly, he wrote a cartoon that it's not Penrose diagram, but there's a horizon appear here, and then there's a creation and annihilation, whatever. Particle, antiparticle are created on a vacuum like this way in the quantum field theory, like this way, and once there's a horizon R, so this is the R direction, and this is 2m, it's a horizon. If you have this antiparticle is created, and antiparticle and a particle created like this way. Once the antiparticle enter the horizon, you cannot come back. So therefore, the creation, annihilation, the particle creation, annihilation does not occur at this point. So therefore, only creation happen, and this antiparticle enter into the black hole horizon at the end. But this guy will just go to infinity at the end of the day. That will give you some radiation. So that's the schematic explanation. Often people just use. I'm not sure, this is kind of controversial, but because it's really. Anyway, some people do not like this kind of explanation and so on. But in any case, there is some radiation, thermal radiation happen from this calculation. Thermal radiation happening from this calculation. And then, and the temperature is given by TH, is given by kappa over 2 pi, and which is, what is the kappa for Schwarzschild? Pi n, like this way. It's like this way. So therefore, it's a bigger the black hole, the lower the temperature. Okay, and roughly speaking, solar mass, it's really small. In Schwarzschild, 10 to the, I forgot the minus, 10 to the minus 8 Kelvin. So the temperature is really small. So the solar mass black hole has 10 to the minus 8. Then most of the black holes are way bigger. So therefore, the temperature is really small. So the thermal radiation equilibrium. usual tempo. So another thing is that the So another thing, so there's black hole will have a thermal radiation. So if you do the thermal radiation, of course the energy will decrease, dE or dt. So there is a, it's called Stefan Boltzmann law, minus alpha and t to the fourth. I think A is the black body. With area A. Okay, so this is called Stefan Boltzmann law. Boltzmann law. Stefan Boltzmann law. This A is the area of the horizon, and then the alpha is some constant. Alpha is a dimension constant. Okay, like this way. And then if you do the approximation, so here we just do the black hole case is something like this way. Minus alpha, area is proportional to m squared. Okay, so m squared. Okay, and then t is proportional to the 1 over m to the fourth. Okay, so that's what you get. And then, so therefore, this is equal to m to the minus 2. So from here, one can just okay. So this is how the black hole will change. So as you the black hole, as you radiate the thermal black hole, it loses energy. Okay, it loses energy. So the black hole becomes thinner and thinner. Okay, and this change of mass is proportional to the inverse square proportional to the m itself. Okay, so then so therefore lifetime is approximately m to the cube. M to the cube become m to the cube, and which is the 10 to the roughly speaking 71 solar mass per cube second. I don't know how long it takes. It's a huge time. To essentially, I mean, once you have a thermal radiation, black hole is thinner and thinner. Okay. And at the end of the day, it just loses all the energy to how to say radiate, give all the energy to the thermal radiation, and it disappears. So it's called black hole evaporation. And the roughly lifetime of evaporation from Hawking calculation is given by like this way. Okay.
What about first or second law of thermodynamics? Area never decreases, right?
That's true. The second law of thermodynamics is like this way, right? Yeah.
How?
Good. That's a good question. So this is a good question. So you have to consider in total. So S black hole is So entropy is in S black hole plus S thermal radiation. So thermal radiation should also have the entropy, okay? Because it's a mixed state, so that you can have the entropy. So the total entropy, if you consider total entropy, it doesn't decrease. Even though if you do the black hole evaporation, so the mass of black hole will change, but you have more thermal radiation. So in total system, the entropy doesn't change, but the here area. So this is really thermodynamic. I mean, it doesn't include any quantum effect. It's a microscopic effect for this one. So here, this one is equal to area divided by 4 plus thermodynamic thermal. Okay. So this is what the total entropy should be. So total entropy do not decrease, but the area, if you include the Hawking effect, can decrease. But if you include this this quantum effect, okay. So fine.
And how it is proportional to the third of the mass, cube of the mass?
I mean, let's see. So you just do the calculation. dm divided by dt is equal to, I mean, some constant times m minus 2, right? So this is the m squared dm is equal to dt. Whatever. Mass is m to 0, right? Yeah. 0 to some number, t star. That will give you t2. Yeah. T to the cube. Okay, so that's the case. So black hole evaporation. There are lots of interesting questions. So the one is that often it's called information paradox. One, information paradox. So you start with the S wave. It's a very big, it's a space-time, and then pure state, S wave. So this is S wave. It's a pure state of psi. And then it has some mass and contracted to the origin, and it create a black hole. It's a Gedanken experiment. So this is a black hole. So it's an S wave with some mass, and it just contracted. You get a black hole, but now it is thermal radiate. Thermal radiate, and then after that you get the evaporation. Only evaporation, black hole evaporation. That density matrix is essentially, as I mentioned, e to the minus beta rho is equal to e to the minus beta en. En density matrix is like this way. En like n Ransdorf order state. So this is called mixed state. This is called mixed state. I will explain what the mixed state means, and so here you just have a pure state, and here you have a mixed state. So, but in quantum mechanics, if you have a pure state, everything is just unitary. But as time evolution is completely governed by unitary transformation by e to the iht. Okay, so therefore pure state has to be pure state as your time goes. But clearly here you have the mixed state. Pure state is involved in mixed state, but that is prohibited by law of quantum mechanics. That's the one information paradox one. So another information paradox is that that I'm going to explain next time briefly. I don't spend the whole time because I mean not all students are interested in this quantum gravity and so on, and then some students are more familiar than I am of this issue. So there is so-called, I will explain, there is so-called von Neumann entropy. So von Neumann entropy is called trace of, I will explain what's the meaning of this one. This rho is a density matrix. You just consider the von Neumann entropy of the black hole. And there is time here. So as you know, so T is the inversely proportional to the black hole. So therefore, the bigger black hole is the cooler black hole. But once you do the evaporation, the black hole becomes smaller and smaller. The mass becomes smaller. So therefore, the black hole becomes hotter and hotter. Okay, hotter. Then if you do this calculation of von Neumann entropy, it behaves like, okay, it depends on dimension, but roughly speaking, it's just increasing, keep increasing. And after evaporation, it becomes constant. So this is the T black hole. T black hole means the time which cost for the evaporate. So this is so Hawking calculation tells that it becomes hotter and hotter. The thermal radiation will give you the more von Neumann entropy. On the other hand, black hole calculation tells you that the S black hole should have the area of a black hole, proportional area of black hole. Okay, but if you just do the evaporation, the area will decrease because the mass is the decreasing. So therefore, so this is S thermal radiation, of course von Neumann, but the S black hole keep decreasing from 0 to. But and the page show that at some point here the quantum effect of the entropy of the black hole should be like this way. Should follow. So this is called page time. And this curve is called page curve. Okay. So the Hawking calculation if you follow the Hawking calculation, what Hawking did is that you fix the geometry and apply the QFT in curved spacetime. But if the thermal the black holes did the thermal radiation and it's smaller and smaller, okay, and then the temperature become big, and the quantum effect become bigger and bigger. Quantum gravity effect become bigger. So this semi-classical calculation Hawking did is black sum, in fact, and there is some strong effect of the quantum gravity effect will just follow in this black hole entropy is decreasing. So this is called page curve. So if you believe the unitarity of quantum mechanics and so on, this yellow page curve should be correct. But the Hawking calculation just show that the von Neumann entropy it just keep increasing as the time goes. So there is something wrong in the Hawking calculation. That's what I'm going to briefly introduce next time. And then, anyway, so if you have a correct way of describing quantum gravity, this theory should reproduce this page curve. So the one information paradox two is that Hawking calculation fundamental keep increasing, but quantum mechanics will tell you that it should decrease at the later time of black hole evaporation. So that's the information paradox 2. For information paradox 2, there is a big progress has been done last 10 years. Some people might have heard of it, like there's an island formula, and so on. I mean, it starts from Liu and Takanagi, and it just roughly speaking. I don't have a time to talk about it. So if you do the evaporation, the singularity disappear, and the people just write down like this way, and then so on. And the radiation will people just at the infinity observer will just radiation in here. You just receive radiation from this observer, but in fact you have to consider something. There is some strong correlation between yellow line and the red line in the state, in the quantum states. Somehow they entangle. There's the same way at the right and left Lindau wedge strongly entangle. Likewise, the yellow line and right region has the strongly entangled. So because it's complement of because the complement of Hawking radiation region. So here, particle and antiparticle creation occurs, but its complement has. If you get rid of this region, so they have to be correlated. So that's the main idea of island formula and so on. But if you include this correlation, somehow one can just reproduce this page curve somehow. So this is a recent, like a last 10 years. It started with 2018 or 19, I don't remember. And then it's a hot topic and so on. So if you ignore this entanglement between island and this radiation region, you will get the so-called firewall paradox and so on. You might have heard of it as this AMPS firewall. I mean, you get a lot of inconsistency if you do not correlate with this island. This is called island, and then this radius region. So those are the recent progress this research community has made. But I'm not going to go into detail. So I try to explain what the page curve means. I try to explain what the meaning of Horn-Lyon entropy, and I will briefly explain a page curve, why page curve has to be the correct quantum mechanically. So that's the next time briefly. After that, I will move back to most likely classical GR. Some people mention a perturbation. Maybe I will talk about perturbation, or maybe some rotational star, like a neutron star and so on. Either I haven't decided yet. But I will go back to just briefly make sure page curve, and then after that I will go back to the classical GR. So which I think, not all students are interested in quantum gravity. Some people are astrophysicists, so I will go back to the classical GR. Okay, so let's stop here.